So I tried to tell you a little bit about how we see Gaia scientifically. I will talk about how did the idea come about and how is our conception of what Gaia is or how Gaia works is still changing. We're still discovering Gaia. So the extraordinary concept we're here to think about originated not by looking at our planet, but because James Lovelock was employed by the space program in their search for life on Mars. But instead of trying to conceptualize looking for life in the small sense of putting an instrument on a spacecraft that would land on Mars, Lovelock made the conceptual leap to think about how would you detect life on any planet if it was abundant. So he took a physicist's view of asking, well, what is this phenomenon of life and how might it manifest itself in a general sense on any planet in the universe? So in that sense, he was concerned with not being tied by the bounds of what life is on Earth, but trying to understand the general properties of life. But he was also always been interested not in life in the narrow sense of organisms or species, but in the sense of the totality of life on a planet. So in the case of the Earth, this is just a diagram about 3 years old, in fact, of the tree of all life extant on our planet. It's what biologists call a clade. And from now on, at least, we're going to use the capital L to refer to all life now and all its ancestry. And when life is abundant on the planet, Lovelock followed the reasoning of famous physicist Erwin Schrödinger and realized that the special thing about life to a physicist is that we're extremely ordered beings in a world that is heading inexorably towards disorder, or rather a universe that is, according to the second law of thermodynamics, heading towards a more disordered state. So in order to be alive, to maintain our extraordinary ordered state, our conscious minds and so on, and not cheat what scientists would call the laws of thermodynamics, organisms have to be powered by a source of what physicists call free energy, ordered energy, if you like, from sunlight, from our star, the sun. And we use that free energy, as we call it, to power this extraordinary organization in our beings. And we build our bodies out of things from our surroundings. And we have to maintain our living state by processing those materials and putting out broadly what we might call as physicists degraded waste products into the environment. So different materials and what we would call degraded energy into our surroundings. So in simple terms, just by being alive, we cannot avoid affecting the world around us, our environment, if you like. And that is a central aspect of our metabolism, as we would call it as scientists. And the important insight Lovelock had was, if this is a general rule of life and life is abundant on a planet, then it must inevitably alter its environment, including its planetary environment. And the obvious source of materials for life and the obvious repository for waste products for life is the air around it, or the atmosphere of a planet. So Lovelock reasoned correctly that whenever there's life in the capital L sense on a planet, it will transform the atmosphere of its planet, and it will leave a signature which, to a physicist or a chemist, we can detect as what we call a disequilibrium in the surroundings. And that should be observable, and in fact it should be observable from a long distance away, because miracles of science. We can see the composition of the atmosphere of other planets by the way it alters the pattern of absorption of radiation coming from that planet. So Lovelock intuited initially, but soon confirmed by observation, that the Earth with abundant life on it has an extraordinary atmosphere, far from equilibrium. The atmosphere that we breathe now is the signature of life. It's got 21% oxygen, which is a real anomaly. And in a mixture with that oxygen are incredibly reactive gases like methane that, as I think you know, burns easily in oxygen, as does hydrogen. And the only way this cocktail of chemicals can be maintained is because living things are all the time creating this chemical combustible mixture. In contrast, our planetary neighbours, Mars and Venus, have a dead atmosphere, the atmosphere you expect just from physics and chemistry, dominated by carbon dioxide. The additional insight Lovelock had in 1965 was that the atmosphere is not just chemically extraordinary because of life, but it is also unusually stable over geologic periods of time. So this chemical cocktail that's highly reactive is able to maintain fairly constant proportions somehow over millions of years. And Lovelock's intuition was that life must not only be creating this chemical cocktail, but also somehow regulating it, somehow acting to stabilize the composition. He shared an office, or was down the corridor from a famous astronomer, Carl Sagan, and popularizer of science. And in conversation, Carl Sagan introduced James Lovelock to the well-known physics of how stars develop. And the crucial point here is that the sun, like any normal star, burns brighter over time. It's a nuclear fusion reactor burning hydrogen into helium. As it does that, the helium builds up. The core of the sun, we say it self-gravitates. But what it does is it makes the core ever so slightly denser and makes the nuclear fusion reaction happen ever so slightly faster all the time. And that makes the sun brighter and brighter over billions of years. This is important for us as life on the Earth, and it's important for us in thinking about the history of life on the Earth, because it poses a huge puzzle. What kept the early Earth warm when the sun was about a quarter less luminous than today? If the atmosphere was the same as today, the early Earth would have been frozen solid, minus 33 degrees centigrade on average, possibly colder. Something has been counteracting this brightening of the sun, and Lovelock again intuited that that something might be life in totality, that somehow by altering the composition of its atmosphere, life may also regulate the climate of its planet, in this case, the Earth. Now, he didn't know how life did that in the mechanistic sense, but that was the core of the Gaia hypothesis, that life in total is involved in regulating the composition of the atmosphere and the climate of our planet. There's another way that arguably Lovelock arrived at this extraordinary idea, and that's because he's the inventor of exquisitely sensitive instruments that he and others were using to detect for the first time all sorts of interesting gases in the Earth's atmosphere that are made by living things, including human living things. So Lovelock was first to detect the great global metabolic reach of living things in the form of these previously undiscovered gases, or gases that we didn't realize were all over our planet. So he used his instruments on journeys across the oceans to show that chlorofluorocarbons were everywhere in the atmosphere, and that these unusual biological gases, dimethyl sulfide, methyl iodide, other crazy chemicals were all over the place, and in fact, in the latter cases, might be playing some role in recycling essential elements back from the ocean via the atmosphere to the land and to other living things. Now, the Gaia hypothesis got its name, Gaia, from a novelist, Bill Golding, the author of Lord of the Flies, a neighbour of Lovelock's in the village he lived in, Barrowchalk, in Wiltshire in England. And it got the hypothesis word, or it became framed as a hypothesis in collaboration with the great biologist Lynn Margulis. And this is one of the few pictures I can find of Jim and Lynn together, probably sometime after they wrote down their original papers on the Gaia hypothesis in the early 1970s. Jim, according to their correspondence, already had the main skeleton of the ideas, but Lynn Margulis brought a deep understanding of microbial life and of history, of the extraordinary history of microbial life on this planet, into Lovelock's kind of physical or chemical conception of Gaia. And that's what really gives the anchor of this hypothesis, which they expressed as atmospheric homeostasis by and for the biosphere. Homeostasis is not a widely used word, even in English, but it's broadly used in physiology to describe an organism self-stabilizing its temperature, for example. And in their thinking and in their papers, something very interesting happens, because Jim and Lynn start to ask questions like, what is the function of this gas, let's say dimethyl sulfide, for Gaia? What is the function of this other gas for Gaia, or for regulating the climate? And they ask those functional questions not in the sort of one narrow, or not in the sense of function just as how does this work, but in what we might call the biological sense of function, as if this is almost like a planetary organism. And this kind of functional talk immediately repelled many scientists, and continues to do so today, because it smacks of what in English we say teleology. It's purposive talk. It's as if there's almost a consciousness, or certainly a purposiveness of this quasi-global organism. And as we'll see, we've spent many decades now trying to explain Gaia in a different way that doesn't just make an immediate appeal to a global being with purposive intent, and instead spent many decades trying to explain Gaia, what I might describe it as from the bottom up, as the consequences of the myriad actions and interactions of tiny microbes and occasionally humans. So there's Jim Lovelock and Lynn Margulis and their proposition. And I mentioned that it upset scientists because of this purposiveness, this intent, this teleological proposition. It also upset biologists, evolutionary biologists, because it's in their theoretical framework, in their way of seeing life, it seemed to conflict with some basic theory in which evolutionary biologists, at least, growing up or writing in the 1970s, 80s, and so on, were absolutely obsessed with competition, with the so-called selfish gene in the work of Richard Dawkins at the bottom right there, together with Ford Doolittle above him. They put Gaia through the lens of their thinking and said, well, this just looks like an appeal to say that organisms are trying to make a better world for each other, and this is what they call altruism in the extreme sense, and it's as if some organisms are paying some cost to make a better world that everybody shares, and this is extremely difficult to rationalize in their fairly narrow evolutionary theory. In truth, Lovelock and Margulis were never thinking in those terms. They were never conceptualizing Gaia in those terms. They were never using the language or the concepts of evolutionary biology. And I think this has persisted as a great kind of misunderstanding of how to see the proposition of Gaia. But it's also proved scientifically somewhat fruitful to try to explain to biologists how something like global stabilization of the climate involving life could come about without requiring this kind of cost-benefit thinking, or this kind of narrow conception of organisms paying a penalty to make a better world for everybody. And it also, the provocation or the accusation that Gaia implied teleology, the purposiveness, that also stimulated Lovelock in trying to build a model to show that these phenomena he was talking about that seem remarkable at a global scale could happen entirely automatically without any consciousness or foresight or purpose on the part of humble microbes or any other humble organism. So Lovelock, in the Christmas of 1981, created what he would call a toy model. He called it the daisy world, and that's because he imagined a planet where the only life forms were light-coloured and dark-coloured daisies, and the light-coloured daisies reflected sunlight, and the dark-coloured daisies absorbed sunlight, and you might say competition or interaction between the daisies for space on the planet could, it turns out, stabilise its temperature. But what Lovelock was doing there is just demonstrating a general idea, which is if we accept that the environment, let's just talk about it as the temperature, has some effect on the growth of life, and there are some temperatures that are too hot for life and some that are too cold and some in between that are just right. That's what that represents. If we accept that that's a general feature of life, and if we accept that life also inevitably alters its environment, and in this case there might be some dark daisies on a planet, or there might be some dark forest in the Arctic that shades snow, that absorbs more sunlight, and the more forest there is, or the more dark daisies there are, the warmer it gets. In other words, if we accept that there's an effect of life on its temperature, and we put the two together, effect of life on the environment, effect of environment on life, then we inevitably start to get some interesting behavior. Scientists like me start to talk about a system that has what we call different stable states. We find we have a system where it might start off very cold with very little life, but as soon as any life grows, it warms things up, and then even more life grows, and we have a self-amplifying situation, and what we call a feedback between life and its environment that propels warming until we get to a situation where it's got a little bit too hot for life, and then there's another stable state where there's a natural adjustment. If you have a little bit more life and it warms things up, that suppresses life, so you return to where you started. Or if you have a little bit less life and that cools things down, that's actually good for life when you're past the optimum. So life regrows, warms things back up, and we always converge back on the other point. So in the daisy world, it looks like this. If you just put black daisies on daisy world and you make the sun brighter over time, at some point the daisies will grow, they'll cover the planet, they'll warm things up. Then as you make the sun brighter slowly, the daisies will die away, but that will counteract the warming from the star. And interestingly, if you mix the black and the white daisies together, you get something a bit more interesting. You get the black daisies flourishing first when the sun is less bright, and you get the white daisies flourishing later when the sun is much brighter. And they're able not only to stabilize the temperature of their planet on the left, but actually to produce counterintuitive behavior. That is, sometimes the sun is getting brighter, and yet the planet is getting colder over time. And that's just a simple illustration that with this relatively crude coupling of life and the environment, you can get things that look like self-regulate, or we would describe as self-regulation of temperature, and very strongly so. So it doesn't require this teleology, and there's nothing un-Darwinian or nothing in conflict with the theory of natural selection in what's going on in this world, except for the philosopher's accusation that somebody designed the model in the first place. So the question then becomes, could this scenario have evolved? And that's sort of the inspiration for some more things I'll try to briefly explain. But basically, for 20, 30 years, with a variety of colleagues, we've been trying to explore with models and test with data and explain how this Gaia phenomenon at the global scale, over billions of year timescales, could have arisen from and be continually arising from life at much smaller scales of space and time, interacting and having these metabolic effects on its surroundings. So that's why I'm going to use these scales of time and space to try to explain how you can go from the small scales to the long or large scales. So scientists know, unsurprisingly, lots of things about the workings of the Earth. They know lots of things about the non-biological or abiotic workings of the Earth and the time and space scales they happen on. We know some things about what we call these feedbacks that sometimes or often involve life but don't have to. And they happen on lots of different scales, including our own bodies self-regulating our temperature, right up to the great cycles of carbon or nitrogen and some feedbacks in those involving life. But then as biological thinkers at least, we talk in terms of selection, or maybe it's better to say filtering mechanisms that lead to certain outcomes being persistent and abundant rather than other outcomes. And that's what I become really interested in, is what are the different kinds of filtering mechanism that could give rise to outcomes that are self-stabilizing up to these long time scales and large space scales. But what we're going to do here is start at the small scales and just think about how could well understood natural selection at small scales start to make a Gaia, if you like. And the thing that many scientists are interested in, and certainly myself, is to try to explain the extraordinary cycling of materials by life. So we are living within an amazing material recycling system that all the microbes and sometimes the plants, trees, earthworms, etc. around us are involved in. On the right, we have the fluxes, the mass per unit time of gases kind of coming out of volcanoes, so not biology. Those are quite meager fluxes. On the left, on a scale in orders of magnitude, we have the exchange of gases at the Earth's surface today. You can't see most of this because these gases are invisible, right? But if you could, you'd be completely awed by these amazing flows going up and down all around you all the time. This is an extraordinary recycling system, and it is the basis of our flourishing and all of life's flourishing on our planet. Because if you try to run a biosphere just with consuming the meager inputs from volcanoes, it will be a tiny millionth of the productivity of today's biosphere. Today's biosphere is flourishing because it's recycling all the materials it needs around and round in the ocean and the atmosphere so it can boost its own productivity, if I may use slightly teleological language. So that has, to a scientist, that has to be understood. Is it obvious that that should be the case? Or is that a surprising thing? So to try to understand that, we build models, for example, or maybe we sometimes make experiments if we can, but in this case it's a computer model. We can see a world in a computer that is like a container of fluid, like the ocean that's being mixed around all the time. We can see the model world with what we call an artificial life form, and that could be initially all genetically identical. And maybe these life forms take in some nutrient that's coming in from volcanoes or whatever into the container, and they make some other waste product, and then they're just limited by the inputs from the volcanoes to the container. But if we allow mutation to happen and we allow new types of life to arise, give it long enough, and we'll get to a situation where organisms evolve that eat other organisms' waste products and derive some useful resource or energy from that. And then they, in turn, excrete different waste products. But we can chance upon the situation where this diversity of life closes a loop where one organism's waste products become another's food until you get round to the food for the original organism, and the materials are going round and round in the system. And then the system is much more productive than it would be if it's just limited by its inputs. And the message we got from playing in the computer millions of times is that wait long enough, and this is a fairly robust or frequent outcome, that you would get recycling of all the materials that life needs. So that gives us some basis for starting to understand Gaia, because even if that were to start at the smallest scales of space and time, it's quite robust, and we observe already in the world around us that that recycling has spread out to much larger space and time scales. But there's more to it. Once we've begun to form these ecosystems, we would call them in biological language, that recycle the materials they need, well, they have other consequences on their surroundings. One of those might, by chance, it might be that some ecosystems make waste products that affect their atmosphere, let's say, or the chemical composition of their surroundings in a way that's good for their growth. That's what I'm picturing on the left. So the total effects of that ecosystem on the left make the environment, called E, better, for the growth, called G, and that becomes a self-amplifying situation. So we get a bigger population, an environment-improving ecosystem. On the right, by chance, maybe another ecosystem's waste products degrade its surroundings, and that suppresses the growth of those organisms. Well, then it's a smaller and less dense population. And then in very simple terms, if sometimes there's mixing between bits of the world, in this case different ecosystems, on average, the environment improving, healthier, bigger population, denser ecosystems will spread at the expense of the environment degrading ones. And we found in our computer worlds that this happened quite regularly, and what it meant was that the environment improving ecosystems came to dominate the world on average rather than the environment degrading ones. This wasn't a universal result. About 10 or 15% of the time, we get what we would call anti-Gaia. We get the totality of life killing itself off by degrading or destroying its world. But the other 85 or 90% of the time, we get Gaia. We get life improving its environment on the global scale of the model. And if you hit the system, it can actually bounce back. It can regulate. It can recover from provocations from the outside. That's encouraging. It gives us a clue as to how it could be that the totality of life might be, on average, improving the environment and might be able to regulate things like the temperature of our planet. But there's some other aspects of our world, like oxygen in the atmosphere or carbon dioxide in the atmosphere, that are well mixed around the planet because the atmosphere is a fluid that flows quickly. And we also see they have stable properties. We see that the amount of oxygen in the atmosphere has stayed near 21% for hundreds of millions of years, whilst all of that oxygen has been replaced, in fact, hundreds of times. And that requires a slightly different explanation, because what I was just talking about was a mechanism to regulate uneven, or we would say heterogeneous variables like temperature, which is different at the equator to the poles and so on. But we need to also explain why well-mixed variables like oxygen in the atmosphere seem to have stability properties. So to try to help in that, we have to begin to think about different and perhaps cruder selection or filtering mechanisms. And we're starting to creep up the scales of space and time, because when we talk about oxygen in the atmosphere, there's an awful lot of it. All of it is replaced about once every 3 million years. That's a pretty long time scale compared to microbes. And yet it has stability properties. So where are those stability properties coming from? So I skipped past a lot of interesting ecology that goes on in the middle scales in order to talk about some crude selection or filtering that could be going on the large and the long time scales. And maybe this idea started in the 1990s in a sort of three-way correspondence between Lovelock and myself and this character, Bill Hamilton, an evolutionary theorist. So you could read his quote if your English is better than my French. But basically, Hamilton started thinking about, well, what if we don't have a population of different things interacting? We just have one thing, let's call it Gaia, but it's got lots of innovation within it, lots of things are changing within it, thanks to the evolution of the organisms within it. Maybe we could have repeated sort of experiments of that Gaia thing over time, and those repeated experiments, there might be some kind of filtering of the outcome of those experiments so that eventually we'd see a stable outcome. That sounds a bit mysterious, doesn't it? But I certainly thought about this quite a lot, and there's a way that there could be a filtering for stable outcomes at a very large scale, if you accept a few basic ideas. So if we accept that life is always evolving down at the smallest scale and is always altering its environment because that's fundamental to its metabolism, then there'll always be new effects on the environment coming about. There's no guarantee that those would, to begin with, lead to a stable outcome. There's really, in crude terms, two possibilities. Maybe by chance they do. Maybe it's like the daisy world and the coupling is right between the environment and life, and you get stuck in a stable, what we call a tractor in the language of mathematics. Well, that's fantastic. The Gaia problem is solved first time around. But maybe the Earth or any other planet is not so lucky. Maybe to begin with, the effects of life on its surroundings, and this time we mean its global surroundings, are actually quite bad for life. Maybe it pushes the planet to a barely habitable state, something we've seen around maybe 3 times in Earth history, the thing called the snowball Earth, where the whole planet is frozen over and we're left with life hanging out in tiny little volcanic hot pool oases in a frigid, frozen world. But that will tend to eliminate most of life, and it might well eliminate the things that caused the trouble in the first place. And then it's just like resetting the experiment, and you can go round again. I mean, life will continue to evolve new effects on its environment. Maybe you have to go round the loop a few times, but at some point, as long as life isn't completely eliminated, at some point, by kind of the laws of probability, we could stumble on a stabilizing outcome. And the crucial point here is that once you have a self-stabilizing interaction between the environment and life, by definition, it tends to persist. you can hit it, and it has some degree of ability to bounce back from those perturbations and maintain the stable state, the little blue dot in a little cartoon. And that's a pretty crude mechanism, but it actually works in a theoretical sense, and it's actually been known about for longer than the Gaia Hypothesis. So it turns out that in the 1940s, this eccentric British character called Ross Ashby, W. Ross Ashby, was not thinking about our planet, was thinking about how do organisms self-regulate, and he was building machines, quite sophisticated machines, to try to understand how that happened at the level of an organism. And he was fascinated also in how the brain might or might not be involved in this. But in simple terms, he showed and made a physical machine to demonstrate the mechanism I just described, that a complicated system that's got a sort of chance rewiring of its interactions can stumble on self-stabilizing configurations, and then they lock in for long periods of time until something comes along and disrupts them. So we have our fancy model of the microbes in a world coupled together, and we find the same kind of dynamics, basically. We find a pattern that basically you do see this coupled phenomenon of life and its surroundings stumbling upon these stable configurations that then persist for long periods of time. And then there are these short intervals of disruption when some new biological innovation means that some organisms can get hold of a resource that's sat in the world and make new waste products in consuming it. And those waste products push the world's temperature, let's say, away from what's good and what everything is adapted to. And then in English, we would say, all hell breaks loose. I hope that's not going to offend anybody in these settings. And what I mean by that is there's a mass extinction. The environment is being driven rapidly away from what everybody had adapted to. Only those who could adapt fast enough survive. And in the middle there, it was almost fatal for all life. But the system just managed to refine stability before everybody died. And then life re-radiated, and there was a long epoch of stability afterwards. I always think of humans and fossil fuel burning when I look at this model. We access this underutilized resource, fossil fuels in the Earth's crust. We're driving the temperature away from what everything is adapted to, and chaos is ensuing. So that gives us a pattern that helps us think about or interpret the history of Gaia, or our planet if you prefer. And we know independently some things about the pattern of the history of our planet. And in simple terms, it fits the pattern of long periods of stability interspersed with short periods of tumultuous change and instability. That's true for the oxygen content of the atmosphere, kind of cartooned here. It's been regulated at 3 very different levels over billions of years. And the transitions between those regulatory regimes, as people like me would call them, were quite tumultuous. There were snowball Earth events, major disruption of the carbon cycle, major turnover of life. I've written about that, but essentially there are 3 times of extraordinary revolutionary change buried in the planet's history. And so the point is, there's something we're beginning to understand here. There's a pattern to Gaia. Time to have some questions, nearly, but one more idea for you. So that seems to be a robust way by which a very crude filtering arrives at sort of self-stabilizing outcomes at the global scale, and then they persist. But there's a little bit more to it, possibly, though there are new ideas that we're still working on, that if you have a way for, let's call it, Gaia to begin to arise, for stability to begin to arise at this global scale, then a planet or a biosphere that begins to acquire that stability and is therefore more likely to persist, will live for longer, if you like, well, it has a better chance of acquiring more stabilizing mechanisms. And that's what the stars are on this diagram. Basically, there's a kind of, in biologist language, a kind of selection just based on persistence alone. If this new Gaia that's arisen with some stabilizing properties is now going to persist longer than planets or biospheres without those stabilizing properties, it's got a better chance to acquire more of them, which will help it persist even longer, and so on. And eventually, if you imagined you were a godlike figure and you could look across many biospheres and many planets, wherever they are in the universe, at some later time, the ones you'd see remaining would be the ones that are Gaias, that have acquired perhaps several of these self-stabilizing mechanisms. And that's what this character, Ford Doolittle, has been concentrating on in recent years as a way of helping explain Gaia. So for what it's worth, we built a model to show that what I just described does work. This selection based just on survival or persistence alone does work as a way of acquiring stabilizing mechanisms or Gaia properties or whatever you want to talk about. So I basically walked you through where we are now on a scientific journey of trying to explain Gaia from the bottom up as a phenomenon. I won't reread that. So I'll just point out that there is something about us humans that might introduce something slightly different into Gaia after around 4 billion years of life. And that is the fact that we have a sort of the staggering beginnings of a collective self-awareness that we're altering Gaia or our planet or the Earth system in a way that might be bad for us and bad for all life or most life. And as far as I can see, octopus are very smart, dolphins are very smart, chimpanzees are very smart, but I don't think any of them are collectively aware of their global consequences of their collective actions. We apparently are beginning to become a little bit aware of that. Whether we're doing anything, whether we're really closing the loop, whether we're really changing our behavior in response to that information is open for discussion. Some of us would say we have changed our behavior because we think the consequences of the way we were behaving were bad for Gaia and we ought to adjust. But maybe it's just a question mark over this, whether humans could add a bit of self-awareness to the Earth's self-regulation, as Bruno put it to be. So Bruno hates the disembodied brain, and I should have changed it, but I haven't got my graphics people to do it. This should be a lot of people in conversation, actually, in this bottom circle. But however we make the picture, if we replace the brain with a community of people thinking about changing their collective behavior, we still have to ask who are the people playing the role, what sort of consciousness could be expected of them, and the question that I liked, which was which lessons might you take or learn from prior Gaia, from everything that went on before we came on the scene, if our collective intention in the room or in the world were to try to help create a flourishing future and a long-term future for billions of people, rather than what we're staring at now, which is if we carry on the way we're going, I can't see this civilization lasting the end of this century. No chance, in my view, on the current trajectory. You can differ in your views, I'm sure you will, but in simple terms, I think I don't think in any sense that we have the power to kill our own species. That would be phenomenally difficult. But this civilization, I think, is really playing with fire at the moment.